We now have a way of relating the electrochemical cell potential to the Gibbs energy change via this equation that we've developed. And what we want to examine in this case is how far we can stretch this connection to learn more about chemical reactions that involve a transfer of electrons. Now, I'll remind you that the Gibbs energy change we could write as in effect the final Gibbs energy content minus the initial Gibbs energy content. Can we do something similar with the cells? Well, that would involve having to create something that amounts to a cell potential for a half cell. So in other words, we could plug in different half cells and determine what their potential differences would be. And that would give us a way of maybe tabulating some of the results so that we could predict in advance what the standard cell potential would be for any combination of half cells. Well, that's what we want to try to explore here. But I will mention that remember that Gibbs energy had no absolute standard. That is to say, there is nothing that sets a zero for Gibbs energy content in a molecule. Similarly, there is nothing that sets zero potential content for a half cell. So we have to use a reference standard in order to establish that. And there's a very common reference standard now that is widely accepted, and it involves using an electrode that has a platinum metal attached in contact with hydrogen gas and acid in aqueous solution. And these are all under standard conditions. So this would be at 1 bar of pressure, and this would be at 1 mole of concentration. And we say that the cell potential for this half cell is set equal to 0. All right, so the whole idea is by setting this one equal to 0, and this is a definition, I should stress, then we can measure the relative potential to any other half cell and then assign that value of that cell potential as the half cell potential for that other half cell. So let me show you an example of how this might work. Let's suppose I took this electrode. This, by the way, is called the standard hydrogen electrode. And it's used in general in these electrochemical things. So this is standard hydrogen electrode. Okay, and let's suppose we hook it up to, let's say the zinc electrode that we used earlier as an example. Okay, now the way I've set this up, normally we would set the anode on the left and the cathode on the right, but before measuring this, we don't know which way the electrons are going to flow, so we don't know yet if the hydrogen electrode truly represents the anode or not. Now, if we go through and we actually measure this potential difference under standard conditions, so this is all under standard conditions, we would find that the cell potential for this particular combination of half cells has a potential of negative 0.7618 volts. All right, so this standard cell potential actually is not positive, so it tells us that in fact the electrons are flowing this direction in this particular case. And we would assign then this cell potential to the half reaction that looks like this. All right, we call this a standard reduction reaction. It's under standard conditions. And this particular value will be the standard reduction potential for zinc. Okay, written as a reduction here. All right, a couple of things about this. These standard reduction potentials are tabulated for all kinds of substances, not just elements, but also for compounds that undergo different kinds of electron transfer oxidation reduction reactions. And so this can be used as a reference in much the same way that we use standard thermodynamic tables with heats of formation or Gibbs energy of formation or absolute entropies to find entropy and enthalpy and free energy changes for different sorts of chemical reactions. We'll be able to use these standard reduction potentials to determine the standard cell potential for any combination of half cells. Now, one thing I'll also mention that you should take as a take-home from this is since the electrons move in this direction from the zinc to the hydrogen electrode, this actually implies that zinc dissolves in acid. Okay, I want you to think about that. If I expose acid to a piece of zinc, it's going to go in this direction and form zinc ions. So the zinc actually dissolves. All right, many metals do dissolve in acid, but this is now electrochemical proof of the concept. All right, so now what I want to do is create a system that is essentially a hypothetical system of two substances. And we'll say one substance is A, and it is oxidized, and another substance B is reduced, in one in the A half cell and one in the B half cell. And both of these have standard reduction potentials. So I'll write that as E0 red for reduction. Both have this measured relative to the standard hydrogen electrode. Okay, or the SHE. Okay, so they're both measured relative to the standard hydrogen electrode. Now, if I were to write down the cell potential for this cell, the way I would write it is like this. I would write it as the potential for oxidation of A plus the potential for reduction of B. Okay, this is the thing that's tabulated, that we have measured relative to the standard hydrogen electrode. Okay, but how would we get this? Well, remember, oxidation and reduction are just reverse processes of one another. So in fact, this will equal negative the reduction potential of A plus the reduction potential of B. Or, I guess, and I'm just rewriting the same thing over and over again, but it's the difference in the reduction potentials between the two. Okay, so this in fact does look a lot like the condition that we had up here for Gibbs energy, where the B being on the right-hand side is where the electrons are going, so that's like the final state for the electrons, and A is the initial state. Now, for this to be a spontaneous process, this has to be greater than 0, so it means that the reduction potential for B has to be larger than the reduction potential for A. So this tells you automatically, when you look in a table of standard reduction potentials, if you were to hook two of those standard half cells together, the one that is higher would be on the reduction side, and the one that is lower would be on the oxidation side. So this one is the higher reduction potential, and this one is the lower reduction potential. Okay, I should put that. Lower reduction potential, higher reduction potential. Okay, the lower one is the one that will be oxidized, and the higher one is the one that will actually be reduced. All right, so this gives you a built-in way that you can assess this when you look at the things that are listed in the table. So let's take a look at an example, because it's always good to see how this works in practice. Let's suppose that I have one cell that is made up of this pair, nickel ions and nickel metal, and I look it up in the potential, in the standard reduction potential table. I find that it has a standard reduction potential of minus 0.250 volts. Okay, I have another half cell that I want to make out of copper that would look like this, and that has a standard reduction potential of plus 0.337 volts. Okay, so of these two, this one is larger, so this is where reduction would happen. Since this one is smaller, in fact it's even negative, this is where oxidation would occur. So if I want to set up this cell potential and cell diagram properly, I would set up the oxidation on the right-hand side, which means I would have nickel, then nickel 2+, salt bridge, copper 2+, and copper. And the total cell potential in this case for this particular combination would be the difference of these two, and so it would be 0.337 minus, well, it's going to be minus a negative, so that'll end up being a plus. I hope you'll forgive my shorthand here. And so we would have a plus 0.587 volts for this particular cell potential. Okay, so this gives you now an idea that we can use these tabulated values. This tells us that electrons move in this direction, and it tells us the propensity for doing that. We could also convert this into a Gibbs energy change by using our standard relationship up here if we wish. In this case, by the way, because there are 2 electrons transferred in each of these processes, both involve 2 electrons, 2 is the number that we would put in here for Z. All right, let's see some further examples when we talk about electrochemical reaction systems.